Hi everyone. Today's topic is steady state heat conduction systems. So after this section, you will be able to know how the plane wall will be available in the steady state heat conduction and what do you mean by thermal resistance and here overall heat transfer coefficient, steady state heat conduction in cylinder, sphere, and also what I mean by critical radius of insulation. So let us start with steady state heat conduction in plane walls. So before going to in detail, let us know what do you mean by steady state. Steady state is nothing but whenever a body is undergoing a transfer of heat, if the properties of the body does not changes with respect to time, then it is said to be in steady state. So uh, now we shall consider how the steady state condition will be applicable for plane wall. In further sessions, we will go with cylinder and sphere also. So now let us consider a plane wall and how we can draw the thermal circuit for this. So now let us take a temporary plane wall like this. If you see this, one side of the having only 20 degrees and the other side it is having 3 degrees. On the top we are having 11 degrees, which means the wall is maintained steadily in either of these directions. So in every direction it is maintaining steady. So now the heat transfer will be, we will calculate. We know the generalized heat conduction equation in generalized heat conduction equation is d square T by dx square in Cartesian coordinate plus d square T by dy square plus d square T by dz square plus q by k is equal to 1 by alpha into rho Cp by dt by dt. We are assuming to be as one dimensional, so d square T by dz square or d square T by dz square will be 0 and no internal heat generation, so it is also neglected. And we are talking about only steady state, so time with respect to time it will be 0. So the remaining equation is d square T by dx square is equal to 0, which I mentioned here. So when I integrate this equation multiple times, I get an equation as T of x is equal to C1x plus C2. Now I have to determine the C1 and C2 constants. So now I taking the boundary conditions, initial at temperature T1 and the length of the body is thickness is 0. At a particular length L, the temperature is assumed to be Ts2. So the boundary conditions apply in the equations. So T of 0 is equal to C1 0 plus C2, which means C2 is equal to T1 and at x is equal to L, we can get it as C1 is equal to Ts2 minus Ts1 by L. So if I substitute the C1 and C2 values in the T of x, I got it as T2 minus T1 by L plus T1. So now if you want to know the temperature at any position, suppose if the length of the element is 4 centimeters, and if you want to determine the temperature at 2 centimeter distance, so I can substitute T of T is equal to inlet temperature, outlet temperature minus inlet temperature by total length plus time, sorry, T1 temperature, so that I can find the temperature at any point. So by substituting this T value in the Fourier law of heat conduction, I can get it as Q is equal to minus Ka by L Ts1 minus Ts2. So if I want to find out the heat flux, what do you mean by heat flux? The amount of heat transfer rate per unit area. So Q of double dash x is equal to Q of x by A, K by L into Ts1 minus Ts2. I hope everyone is understood. So now we shall go with what do you mean by thermal resistance? Why to study this thermal resistance? So we all know that the electrical resistance is nothing but conducted with respect to electricity. So thermal resistance is related to heat. So we all know the Ohm's law, that is I is equal to V by R. Similarly, for conduction we know that Q is equal to minus K into by dt by dx. Here the elements of the particle will be not changes, only the temperatures will be changing. So thermal resistance can be written as Ts1 minus Ts2 by Q of x, where Q of x is L by Ka. So this L by Ka is nothing but your thermal resistance. Similarly, for convection, it is 1 by HA. Okay, so if we are having a circuit with one conduction and two inlet side and outside, we are having a convective mode of heat transfer. Then there is a called a new term that is called as overall heat transfer coefficient. So we have to take both the convectives and also the conductives. So the net heat flux will be at first body it is T1 minus d infinity by 1 by HA as it is convection on the left side, and within the body it is conduction, and the third is convection. These three heat transfers will be equal. So the thermal resistance R total is equal to 1 by H1A plus L by Ka plus 1 by H2A. So the total will be change of inlet minus outlet. So T infinity 1 minus T infinity 2 by R naught. Okay. If it is we are having some multiples of conduction walls, so then it is T1, T2, T3. So here we will be taking as Q of T outlet minus T inlet minus T outlet by total summation of R, where R will be how many modes of heat transfer are there. We will be adding all the thermal resistance. So this is your formula, and this entire formula with respect to temperatures is with respect to convections and conduction states is called as U. Within the composite system, it is often convenient to work with overall heat transfer coefficient, which is given by Newton's law of cooling, that is Q is equal to UA into delta T. So this is your final equation. So now let us go with radial system, that is hollow cylinders. Similarly, what we had done for a plane wall, now let us take a composite, a hollow cylinder. So for that I want to know what is the generalized heat conduction equation for cylindrical coordinates. I know that 1 by dou r, 1 by r into dou by dou r, k of r dou t by dou r plus 1 by r square, dou by dou phi, k r to dt by d phi plus d by dz, k into dt by d plus z is equal to rho cp into dt by dt. So we all know we are assuming as one dimensional, so phi and z will be 0 and no internal heat generation and steady state. So this will also be 0. So 1 by r into dr by dr, kr into dt by dr is equal to 0. By taking two integrations, I can get it as temperature of r is equal to C1 ln r plus C2. So if the first integration you will be obtaining as d by dr of kr into dt by dr, and further integration it will be minus 1 by r. So it will be ln of r. So the boundary conditions I assume it to be outside radius at r1. Okay, at r1 radius the temperature is Ts1. At the r2 radius the temperature is assumed to be Ts2. So if I substitute the boundary conditions, Ts1 is equal to C1 ln r1 plus C2. Ts2 is equal to C1 ln r2 plus C2. If I subtract 1 minus 2, I can neglect C2. So TR is equal to T. First I will get C1 TS1 as TS1 minus TS2 is equal to C1 ln of R1 by R2. On further simplification, I can get it as T of R is equal to TS1 minus TS2 by ln of R1 by R2 into ln by R2 R by R2 plus TS2. Okay, this is thermal resistance for multiple serial radial system. Similarly for sphere also, actually this is out of the syllabus, but this is your generalized heat conduction equation. So we will be considering only the first term because we are considering only in one direction. So the second directions and third directions will be 0 and assume it to be steady state and no heat generation. The simplified equation will be like this. On integration of this, I can get it as Q of R is equal to 4 pi k into Ts1 minus Ts2 by 1 by R1 minus 1 by R2. Try practice this so that you will be very helpful for your further guidance. So next is critical thickness of insulation. So we all know the insulation will be done in only electricity for saving the energy. Similarly, this critical radius of insulation also used in heat transfer, which was installed in round circular pipes or cylinders. The inner temperature is fixed and the outer temperature is exposed to the environment. So We know that Q is equal to 2 pi L into Ti minus T infinity by Ln of Rn. If I integrate with respect to the resistance R naught outer radius, the simplified equation will be like this. So as R1, R2 are all are constants, the remaining terms will be K by H. So the critical thickness of a cylinder is taken as K by H. For sphere, it will be taken as 2 times of K by H. So these are the some shortened essays answers which are asked in your previous examinations. Thank you.